although you will learn Java, this is not primarily a Java course. You'll learn a lot of Java, but I hope what you learn will be more universal than Java in particular. And although you'll learn object-oriented programming techniques, I'm hoping that you will learn, A, how to apply them to other situations, and we'll learn good programming techniques and what to use when. So the course is divided into 3 major sections. The first is the basics of object-oriented programming in Java, where we'll talk about structured control, classes, inheritance, the basics of Java, the first 6 chapters of the core Java book. And we're going to do that this week. So your heads are going to explode. Because you need basically that to do anything in Java. You basically need that to do Hello World in Java. So after that, we're going to talk about common programming situations, environments, things that you need to know if you really want to be a practical programmer, as opposed to just knowing object-oriented programming and how to do a lot of classes. There's a lot of real situations and things that you need to know about programming. So we want to cover, there'll be a section where we cover per lecture I/O programming and streams. We'll do exception handling, event-based programming, GUIs, network programming, multi-threaded, some notion of asynchronous and reentrant programming. Basically, these sorts of techniques. I mean, there's nothing really deep in any of them, but it's good to see them, to know how to do them, and your future employers will be grateful. Kind of interleaved with that, and towards the end, we're going to talk about some advanced concepts and ideas which are mostly going to be cultural, and that we're not going to be able to incorporate them into the problem sets and projects because we just don't have enough infrastructure, and there's just too much stuff. But there are also things you should know about. Plus, you'll be working on projects by then and just will not be ready to incorporate new information. So things in that category are going to be things like component models. Everybody should have some idea of binary component models, how to do object-oriented programming in C++ and C. We'll do a brief thing there. Internationalization, serialization, web programming. We'll do some servlets, JSP, applets. Also, some more philosophical topics on design, what object-oriented programming is. There's a whole mess of design methodologies around object-oriented programming. We'll look at some of that. Maybe some UML, Unified Modeling Language, some design patterns. There's all of these fads out there, design patterns, anti-patterns. I think the best named one is extreme programming. Seriously, there's a book and a technique. So we'll talk about some of that. Which brings me to object-oriented programming, which all of the object programming books that you'll see is probably start out with a manifesto about how object-oriented programming is the greatest thing since sliced bread and the savior of the world. And usually they start out by building up some straw man of how to do it wrong, and they call it structured programming or something, which was the last fad that was going to come along and save the world, and then argue about how object-oriented programming is different. I think those manifestos are a little bit unfair, and in some sense meant to flog languages or philosophies. You can argue endlessly about programming style. But that is not to say that there are not some good ideas in object-oriented programming, and I'm going to try and keep the course relatively philosophy-free and just concentrate on the ideas and not even tell you the difference between what are structured programming ideas versus object-oriented programming ideas versus other ideas, because there's no reason to teach you the wrong way to do things just to contrast it with the right way of do things. Hopefully, the right way to do things will just seem natural. Let's see. Let me say a few words about the text, going back to administration for a moment. I had them get you Core Java and Core Java 2, and they've got volumes 1 and 2, which is good. We will do pretty much, I think we'll do all of Volume 1, and we'll do about half of Volume 2. The other half of Volume 2 that we won't do is mainly reference for the graphic stuff and the graphic user interface stuff. So there's 2 very long chapters which are good reference material, but kind of tedious to go through piece by piece on the board. So we will gloss over those, but you'll undoubtedly use those chapters. Let's see, there's in the syllabus, which I will eventually upload, there's readings associated with most of the lectures. Today is basically chapters 1 to 3. Don't get too concerned about that. Chapter 1 is kind of an introduction to Java. Chapter 2 is, I think, a little bit of manifesto. And then Chapter 3, you actually get into the programming content that we're going to cover today. If you don't like Core Java, I like Core Java because it is both a good reference and a good kind of learning tutorial book, though it does tend to assume that you come from a C++ background rather than a Scheme background. So if you want another source, there's another book which is good to have called, or good to look at, Thinking in Java by Bruce Eckel. It has the advantage that it's free. You can download the HTML or PDF from the web. You can go to bruceeckel.com. In the handout I'll put up on the web, there's a bunch of pointers to interesting sources, and this is one of them. Or you could just go buy it. I think anybody who gives stuff away free deserves some, to have their book purchased.
How does he spell his name?
Eckel, sorry. Finally, if these two don't do it for you, we have Mr. Bunny's Big Cup of Java, which is the follow-on book to Mr. Bunny's Guide to ActiveX, which was... So this is almost completely devoid of facts, but is nonetheless... although not as good as Mr. Bunny's Guide to ActiveX, which was brilliant, it's nonetheless, when you've read enough Core Java, you need to look at this a little. I'll leave that lying around. Okay, so let's see. Let me talk about Java a little bit. Since that's the tool we're going to use. Java is an object-oriented language developed at Sun Microsystems, and in its short and glorious history, it's been remarketed a number of times. It was originally designed, I guess, for kind of digital appliance communication. They eventually renamed it and retargeted it to the web. So originally when it came out, there was a lot of fanfare and hoopla about applets. That was kind of what Java was all about, this platform-independent, secure applet platform. That was kind of Java mid-90s. I feel that's kind of died out a little. You don't hear a lot about applets these days. You don't see a lot of applets when you are browsing the web. And lately, Java has gone kind of in 2 directions. They've pushed it for a platform for enterprise middleware software for basically enterprise programmers to go out and hook databases and build business software. And the argument there being that you can do this stuff faster and better and whatever. The other place, and I think this is where most of the Java action is these days, is in server-side web applications. There's a lot of stuff going on with servlets, which are kind of the server-side version of applets. Java classes running on the server. They hook in with these Java server pages, which are kind of the Java equivalent of Microsoft's active server pages, ASP. There's a lot of stuff going on with Java and XML on server-side. The Apache group has come up with a lot of neat stuff, and they put out a lot of their stuff in Java. So I think currently that's where Java is headed. It may or may not make it as an enterprise platform. Part of it is part of the limitations. I mean, the advantage of Java, what it was touted for, is that it's platform independent. You can write once, run anywhere was their slogan. That, after Microsoft got through them, turned out to be not quite as portable as everyone would like. There's also been also the issue of performance. Since it is, the way Java works is you start out with a source file, you compile it into a class file, which is actually bytecodes for a Java virtual machine. So then you have to start up the Java runtime and interpret this. So that interpretation step basically makes everything run slower. And people have quoted anywhere from 10 to, probably from 5 to 30 times slower than an equivalent program written in C. So that's pretty slow. Now, if you talk to Java converts, they'll tell you that, first of all, speed doesn't matter because you're writing GUI programs that you're typing at, and you're waiting for the user, or you're waiting for the network, or you're not computation bound. So that's it's not an issue that it runs slow. Or they'll say that you have these just-in-time compilers or binary compilers, which will take the Java code and compile it down to native code for the machine, and therefore you can run as fast as C. And then when you ask them, can you really run as fast as C, they say, well, what we mean by as fast as C is 30% slower than C, because there are some things that are built into Java which keep you from writing, from doing bad things, but nonetheless get in the way of pure speed. So I think that is currently a limitation for Java to really make it into certainly the shrink rack software. If you buy something off the shelf, you certainly want it to go as fast as possible, and or if you're a server, you're something that you can run as many copies of at the same time on a machine. So the future of Java is, who knows? Who knows? The reason we're using it is that it's a very good environment for learning object-oriented programming and programming in general. Although it's not kind of optimized for speed the way that, say, C or C++ are, certainly, it prevents you from doing a lot of very nasty things that and have a lot of nasty bugs that you can get into C and C++ for doing very clever things. So it's kind of a very protective environment that nonetheless lets you have all of the concepts and power of this sort of programming. So C is very primitive. It's kind of like a bunch of very, very sharp hand tools where you can easily cut yourself. Java is more like it's like Norm Abrams' workshop. It's got every power tool you can possibly imagine, but they're also a little dull, so you can't hurt yourself. C++ is kind of a workshop of very sharp power tools with no safety guards. So let's see. Another thing about Java is when you talk about Java, there's really kind of three things to talk about. One of which is the language Java, which is the syntax and the basic structure. The second is the huge library set that go along with Java. A lot of what we're going to learn in this course after the first week is essentially the libraries that people that are part of the Java system, which do a lot of things for you that in more primitive systems you would have to build by hand. And it just makes stuff like network programming much, much easier than it would be in a less library-oriented environment. And the third piece of Java is the runtime system. And we're going to use the runtime system from Sun, but you can use different compilers and runtime systems and whatever. So there's really these three components of Java. So it's not just a language.
What's the runtime system for?
Well, the runtime system is essentially the interpreter. When you write a Java program, you start out with a source program, a .java program. That gets compiled into a .class program, or a .class file by the Java compiler. And then you run that in this Java runtime by typing Java, class name, maybe some arguments. And that reads that class file and then interprets that inside the Java Virtual Machine, loading any other classes that references on the fly. So it's just a slightly different model than, I don't know how much C programming you've done. It's probably closer to a scheme model because it does do a lot of dynamic linking and loading.
No one's written like a straight compiler for Java that would skip the virtual machine?
There are both full binary compilers for Java and what's called just-in-time compilers. The problem with the full binary compiler is you've got a target for every machine. Okay, so if you have a source on the web, you've got to, right? So the just-in-time compilers are supposed to take the .class file, and if there's a just-in-time compiler on the machine as it's running, okay, it compiles frequently used bits and loops and stuff, and gradually compiles replaces the bytecodes with calls to native code. So there's lots of claims that say this is fast. It's as fast as full compiled languages. Benchmarks. In preparing for this course, I searched the web for benchmarks, and they are hard to come by. If I list some of the languages which certainly I encounter and probably form the basis of what's out there. There's C, C++, and let me rank these or comment on these on a number of dimensions. We can talk about performance, how fast the code goes. I'm going to abbreviate. Ease of use, this is essentially how fast the programmer goes. Okay, there's kind of two parts of programming. First of all is when you get the product done and debugged, how efficient is it and how fast does it run and how little memory does it run in. Then there's the other side of programmer efficiency is are you ever going to complete the project and how long is it going to take you to complete the project. So some languages are optimized for this, some languages are optimized more for that. An issue we'll talk more about today is typing, whether variables are typed. Other criteria that languages differ is storage management, how they do storage management. When in Scheme, you had a garbage collected system where you could allocate stuff and it would just magically go away for you. And you'll be pleased to know that Java works the same way. But there are lots of systems that don't, where you have to basically keep track of every piece of memory on your own. And the third piece is whether it supports objects, whether it's object-oriented. And some of the languages to look at are C, C++. If you do any numerical programming, Fortran is probably big. COBOL is actually still very big, but I'm not going to write it because I'm hoping you will not be unfortunate enough to encounter it. But these are all meant to be very high performance on the runtime when you finally get done. But in terms of programming, they're kind of low to mid. C and C++, generally strong typing. C less so than C++. You can do a lot of nasty things with types in C. And get yourself in trouble or do some cool stuff. And these are, let's call it explicit storage management. Here, you're in charge of keeping track of every little piece of memory. And one of the hard parts of writing C, C++ programs is avoiding memory leaks, because you're allocating stuff off the stack, you're passing it around, you've got all these modules. You've got to make sure that your program doesn't grow and grow and grow and grow as it runs. And that's fairly tricky to do. And certainly objects, C++ does. C is the non-object-oriented version. Let's see, there's kind of another class of languages, which I grouped together, though in some ways they're quite different. Java, Visual Basic, maybe I'd put Scheme in this category. Performance, I'll say low to mid. Certainly in the non-compiled phase, these are not going to run nearly as fast as these. Visual Basic is the basic scripting language, by the way, of a lot of Microsoft technology. So if you're a Windows programmer, you undoubtedly do a lot of Visual Basic. Almost nobody does a lot of Scheme, unfortunately. So ease of use, from medium to high. Visual Basic is very easy to cobble together a graphic user interface to do fairly sophisticated things in a short amount of time. That's basically what it's designed for. Java takes you a little more effort to put together a GUI, certainly, but scales better to large applications than Visual Basic. And they're probably both easier to use than C and C++, certainly. I think these are all strong typed, except for Scheme, which is runtime type. So you don't have to worry about compile time typing. Presumably that's true, right? You didn't have to declare everything typed in C. And finally, both of Java and Visual Basic are very, very object-oriented. It's hard to do anything in Visual Basic unless somebody's given you a lot of objects to use. Scheme, I guess there's an object system in there somewhere. At least there's probably one you can use. But finally, there's storage. Let's see. Java is garbage collected. Scheme is garbage collected. Visual Basic, to be honest, I'm not sure. Since it is so highly component-oriented, it's basically pulling in and scripting a lot of binary components. A lot of the storage management is happening in the components themselves. So I suspect it's not GC'd. There's another class, which are scripting languages, which are, have the danger of kind of overwhelming some of these. There's JavaScript. There's a scripting version of Visual Basic. There's Perl. And what else do I have? Tcl. Ars Digita uses Tcl extensively. Perl is extensively used in web programming and writing shell scripts and just utility programs to do various things. JavaScript is currently used in client-side scripting for web pages. One thing to point out is that Java and JavaScript have almost nothing in common, except the first four letters of the name. They are not the same language, nor is JavaScript a scripting version of Java. The naming came about, I guess, through a marketing agreement between Netscape and Sun. This was originally called LiveScript, and when Java was hot, they made a marketing agreement and changed the name. The only real thing they have in common is that kind of Java, JavaScript, and to a lesser extent Perl have all adopted C syntax, which is a nice feature since once you learn one of these languages, you can pretty much learn the syntax of the others. Yes?
Could you explain exactly what it means to be a scripting language?
Scripting languages are very high-level languages which have, they're not geared towards efficiency in the traditional sense of you wouldn't want to write a large program in them, but for doing small tasks like reading a whole mess of files, opening a whole mess of files, reading all the lines in the files, and changing all the Q's to S's, okay, which sometimes you want to do. Write a C program or a Java program, to do that, it's going to take you page after page after page. Whereas you can write that whole program in Perl, just to show you what Perl looks like. pretty much is a Perl program to convert all the Q's to S's in all the files that you give it at the command line. So the advantage of it is you can write really compact programs extremely quickly. The disadvantage is that if you look at somebody else's Perl program, it looks like this. And you just, it literally looks like that. And you can never figure out what, on even stuff you wrote 2 weeks ago, you'll never understand again. So Perl, but on the other hand, it is just wonderful for doing file manipulation and filtering. And also, it's, there's a whole, it's very highly used in CGI programming with Apache. JavaScript, as I say, looks very much like C. But these are generally low performance, but very easy to use once you learn them. They're generally untyped, so you don't have to worry about typing at all. You just say, write down kind of, they're written in such a way, they're written by programmers for programmers, so that if you just kind of write down what you want to do, it'll generally work, because somebody's already thought about it, thought about how they would write it down, and built the language so it does what you want, which is kind of nice. These are all, well, generally garbage collected, and I would say they have object packages associated with them, but they are very weak object packages. So I wouldn't call them full object-oriented languages. So this is kind of the space. Java is kind of the midpoint in this performance spectrum and ease-to-use spectrum. It doesn't have, for some things, it's much harder to use than, say, Perl, but it's certainly much easier to use than C or C++. It does have strong typing, so this is one of the differences between Scheme that we're going to look at. On the other hand, it's still garbage collected, and it has a strong object package. So let's see. We're about halfway through. Why don't we take a break? I'll erase this. Don't go wander, just like stand up for a minute. And then we'll actually start on learning, we'll do chapter 3. The second is the syntax is kind of reverse of what you see in Scheme. Instead of prefix parentheses notation, it's basically infix notation, and it's a curly braces semicolon delimited language. There's a whole class of languages that copied the syntax. So the basic delimiting thing is semicolon or curly braces, which unfortunately I can't write very well. And all statements, the statement terminator is a semicolon. So at the end of every statement, you'll get one. Philip calls this cancer of the semicolon, but I think that's unfair. Let's see. Lexical scoping. Did you deal with this in Scheme? Is Scheme lexically scoped?
Yes.
OK, because in some Lisp variants, you can get into some very hairy dynamic scoping schemes, which ultimately don't do you any good. But on the other hand, there is not many levels of lexical scoping. You can't define routines within routines within routines. So the scoping from a procedural point of view is pretty straightforward. You can you do have to worry about scoping with respect to classes and scoping with respect to what are methods, which is what we call procedures in Java and object-oriented languages. You have to worry about keeping all that scoping straight. But once you get the hang of it, and if you write clear programs and don't give all of your variables the same name, it's usually pretty clear. Let's see. In terms of style, there's definitely, for these types of languages, a bias towards and support for iteration versus recursion. Your first approach to doing something in Java or a procedural language like C is not the recursion approach. There's some programs which very naturally lend themselves to recursive solutions, but there's good support for iteration for those. You typically wouldn't write tail recursion to do iteration. You'd write real iteration, and there's a lot of flexibility in there. Finally, the heap storage, I think, is quite a bit more visible than it is in Scheme, certainly than it is in Lisp. It's only half as bad as it is in, say, C or C++, so you only have to worry about allocating the stuff. You don't have to worry about getting rid of it. The garbage collector will get rid of it. But you do have to explicitly allocate everything and often make sure it's the right size. So, all right, well, let's go through each of these things, or start through the language. The first thing you need in a language is variables. And variables in Java are typed, and which means you have to declare them before you use them. So typically, anything in Java will start out, a method or a class will start out with a curly brace, which is our delimiter. So we won't worry about what this is, but it's something delimited by curly braces. And the first thing you want to put after your curly braces is typically your variable declarations and definitions. And so you start out with a type declarator, then a variable name, we'll call it count, to get a pleasant change from foo. And an initialization, and of course, a semicolon. So this is your basic variable declaration statement. It incorporates, in some sense, two different things, which in other languages are separated. One is a definition of the variable count, the fact that count is a variable of type int. Okay, that's what this is telling you. It's also defining the variable, which means it's not only a variable of count int, it's a variable of count int in this scope kind of here in your program. There's some languages which lets you define count over here and declare it over here, and then you can initialize it anywhere. Java and most languages allow you to do initialization. Yes?
I'm sorry, could you switch it into from your pocket? Yeah.
How's that?
That's good. Thank you.
Allows you to do initialization of the variable in the definition statement. It's almost always a good idea to initialize variables, especially reference variables, which we'll talk about later on. Otherwise, you'll undoubtedly get these null object reference errors propagating up from Java libraries, which will drive you nuts. So always initialize your variables. One thing, all right, we'll talk about this later. So these are variables we're doing more or less think of them in procedures. We're talking about building procedures the way you would in Scheme or C, but since we're in object-oriented programming, they're called methods for reasons that will become clear tomorrow, and I'll just use the term method from now on. Okay. What else interesting can I say introductory? Comments. Comments are good, and they make your code easy to understand, hopefully, for people who follow you. And Java supports two types of comment. One is an end-of-line comment. So anytime you see a double slash, everything that follows that is a comment. And you can use that at the beginning of line, and some people make little artistic things. And the second form is it also understands C comments, where you have a slash star, and then text, and then star slash. And this can be multi-line or single line. And everything in here is basically ignored. If you're writing, just for stylistic purposes, if you're writing like a paragraph at the beginning of text, most people put a line of stars just to make it clear that it is a whole comment, though these aren't necessary. Comments do not nest cleanly. They might in Java. They certainly don't in a lot of places. So avoid in your comments any further use of those. So otherwise, you'll drop out of your comment unappropriately. These, I believe, do nest. So if you have that later on, it's still considered a comment because it's just to the end of the line. So let's see. All right, so I've mentioned this new concept of type. Types are good. Types are used by the compiler to perform error checking. Types are basically designed to keep you from trying to add 3 to a string or to, multiply 2 arrays together. Or to basically perform inappropriate operations. Some people like to present an abstract view of types that they represent partial information about the value space that you have. When I say integer, it's a number. There's actually a defined range of number it is. It's not a floating point number. It's not a string. So the compiler can do quite a bit of reasoning about what is a legal operation and what is not a legal operation just based on that. Beyond that, it is, I think of it more as kind of just a string identifying this type concept. And there are rules for manipulating types, and the compiler knows them, and you only have to know a few of them. But a second thing that type does, especially our basic types, is they allocate a piece of space, in this case on the stack. If we're writing a method, a procedure, integer is says we're allocating a specific size piece of memory, okay, which is going to be interpreted as a number in a certain way, but it's also a certain size, so that controls the range of the number that you can that you are allowed to put in there. So let's see. Java has a number of built-in types, and let's just go through them, starting from the shortest. Java has a Boolean type, which takes 2 values, true and false, which I believe are reserved keywords. And there's some operators which only operate on Boolean types. It has a bunch of, let's see, this is a class of numerical types, which starting again from the largest or smallest to the largest has byte, which is your basic 8-bit 1-byte unit. So it can hold a number between, this is a numerical type, remember, so it holds a number, and the number is between plus 127 and minus 128. Numerical types in Java are all signed. There's no unsigned number type. So it's basically plus and minus 2 to the n minus 1. So there is short, 2 bytes. There is int, which is 4 bytes. Be a little wary about int in other languages like C and C++. Int is defined to be kind of the native default, most efficient integer size for the machine. So on old 386 machines, ints were 2 bytes. On 486s, they are Pentiums. They're 4 bytes. On some machines, they could be 8 bytes. But in Java, ints are always 4 bytes for consistency. There's also long, which in Java is 8 bytes. So these hold integers. Int is by far the most useful because it's big enough that you typically don't overflow. And if you worry about overflowing, you probably want to go to infinite precision arithmetic as opposed to just going to long. So anything you have a counter, this goes from about plus or minus 2 billion, roughly. Okay, so then there's some types to represent floating point numbers or an approximation to real numbers. So there's a float type, which is 4 bytes, and these are IEEE standards. So the same format should work everywhere. 8 bytes. Okay, these represent decimal numbers, 23.456. Now, one thing to notice, which they've probably gone over in other courses, is your 4-byte integer, okay, and your 4-byte float has the same number of bits. So if you think about it, they can only represent the same number of things. All right. Now this is giving you integers between, say, 2 billion and minus 2 billion. This is taking those bits and interpreting them as kind of decimal numbers strangely distributed through this space. So you basically get a choice of, you get a certain number of digits of precision, and you get a choice of where to put the decimal place. But you don't have infinite granularity on this thing. So you really only have the same number of numbers that you can represent. They're just the same. They're just interpreted differently and spread out over the real line in different ways. So, so it's just something to be aware of, that these are not infinite resolution numbers. So you always, when you're doing floats and doubles, making an approximation, and you want to have all your algorithms, make sure you're aware of that.
What is a double?
Double is a floating point number with 8 bytes. It basically just gives you twice as many decimal places, or twice as many significant digits, is probably what I should say. Let's see, this one probably gives you about 8 significant decimal digits. This probably gives you around 16 or 15, depending on how much they put in the exponent. There's a character type, okay, which represents characters. And characters, let's see, the numbers, if you represent them literally, they just look like numbers. Floating point numbers are represented as regular decimal expansions. I believe this will, by default, be considered a double. So if your compiler complains and you don't want it to be a double, you may have to cast a constant to a float. So the syntax for character constants is single quote. So single quote C is the character C. Characters, although you never have to know this, the size of character in Java is 2 bytes. And internally, Java uses Unicode encoding. Okay, we'll talk about that probably in a couple weeks. Right now, assuming we are all native English speakers, or at least English programmers, just assume it's English character set. And so the things that you can put in the single quotes are normal ANSI characters. Let's see. So character type, and it only represents a single character. So, finally, there is a type called void, which is very useful and is basically no type. It has no values, and but is used to, for example, declare methods. If you have a method that you write that's not going to declare a value, you declare it as a void method to tell the compiler that it's not going to return a value. And then later on, if you accidentally use it to say, foo equals my void method, it's going to complain and say, this doesn't return anything. So you'll see lots of voids. These are pretty much the basic types, the basic built-in types of Java -2, I guess. There is a built-in string type, which we'll talk about tomorrow, since it's kind of a hybrid type. And then there are arrays of all of these types. And hopefully, your recitation instructor will do a fabulous explanation of arrays, since that is his topic for today. Arrays and reference variables. Also, at the very bottom, not in importance, but there's also lots of object types, which we'll talk about tomorrow. So object, yeah. All right, I'm going to move down to the board. Once we have our variables, we need to do something with them. And the first thing you want to do with them is expressions. You need to combine them to make other things, to do computation. And you do this in Java with operators. For example, expressions, well, let's see, the basic, say I have int count. All right, so basic expression syntax is, if you want to do the BNF, it's kind of expression op, expression dot, dot, dot. So it's infix notation. Instead of being plus AB, you write argument, operator, argument. And it works pretty much the way it works in math, okay? If you can read math, you can pretty much write this stuff. This just computes a value, which is count plus 1. So if count is 1, it computes the value 2. It doesn't do anything with it yet, because we haven't done any assignment. We've just done an expression. So expressions take a bunch of variables or constants of a certain type and compute something else of a different type. And the types on either side have to be consistent. So before I go through some examples, let me just list some of the operators or operator classes. We have your normal arithmetic operators, which are plus, minus, times, division, percent. And these are, excuse me?
That's modulo?
Yes. These types go from a numerical type to a numerical type. So they will take int or char or shorts, combine them together, and compute another int or temp or short, or they work on doubles, just the way you would expect, and floats. And in particular, Java is pretty smart about if you combine, it's going to let you combine, say, ints and floats, and it's going to combine them into the most precise level or most precise type it thinks. So it basically was going to try and promote these types to these types and smaller types to larger types in the numerical range if it has to. It's going to keep everything in kind of the smallest size it can, but if you combine, if I do count plus 1.1, okay, the resulting type of this expression is going to be a floating point or a double. Conversely, if I try and assign something like a floating point or a double number like 1.1 to an integer variable, something's got to give, because I've got this 0.1 that's not going to make it into the integer. And so Java will probably complain if you try and do that in the compiler, but you can say, yes, I really want to do this in, again, the source code, and it will just round it off for you.
Will rounded or will it truncate?
I believe it does rounding, though I could be wrong. If you're taking advantage, if you have to know the answer to that question, you're doing something wrong. Let's see. The next class is logical operators, which take, in general, a numerical expression and produce a Boolean. And these are things like equal comparison. Java uses equals equals, as does C, for equality test versus assignment. Over here for assignment, we use single equals. For logical equality, we use double equals. This is generally EQ in the Lisp sense or scheme sense. And one of the classic C bugs is to accidentally use a single instead of a double equal sign in an if statement, which makes the condition always true, or almost generally makes the condition always true, and really screws you up for a long time. Java actually catches that in particular and does not let you use single equals in a conditional statement. Not equals, the syntax is bang equals. Then you have greater than, less than, as you would expect. Greater than or equals, less than or equals. That's about it. All right. So actually, I probably misnamed these. I apologize. Let's call these comparator operations. Comparison. Logical is really a different class, which are Boolean to Boolean, okay? They're the classic logical operators that take Boolean to Boolean, and these are a challenge for my writing ability. I'm not very good at ampersands, but double ampersand, double vertical bar, and caret are your logical operators. This one is logical and. This one is logical or. This one is logical not. So one way to write, A is not equal to B is the expression A not equal to B. Another equivalent way is to say not A equals B. So this one is using a not equals comparative operation. This one is using the equals comparator, but then inverting the logical case. And if you studied, presumably in 6004, last term's course, the De Morgan rules for expanding nots over ands and ors and all that sort of thing. So if you have complex if statements, you sometimes can use those to simplify things. Let's see. Another class of operators, much less frequently used, are bit operators. Right? Bit operators take these numerical types and treat them as a bit vector and let you play with individual bits in the bit vector. This is almost never a good idea, unless you're doing, unless you're writing device code or getting things from external sources where each bit has been assigned a individual identity. So they also tend to overuse the symbols, but they mean different things. Let's see, that one. All right, so this is again, AND operation, but it's bitwise. Okay, logical takes a true and a false, and if you AND them together, makes a false. Bitwise AND, okay, goes bit by bit and sees whether the bits are 1 and 0, and basically ANDs each bit together. Okay, so this is OR. This one is, I'll call it inverse. It's really bitwise NOT. If the bit is a 1, it'll turn it to a 0, so flips all the bits. These guys are shift operators. They take all of the bits in your number and shift them 1 bit to the left or right. The one at the end, if you shift to the left, the one at the end gets stored as, basically you get a 0 at the end. If you do a shift to the right, I believe it sign extends. So you get a number of the same sign. All right, then there is a set of assignment and side effect operators. Very, very useful. Certainly in Java programming and procedural programming in general, you don't have a terribly functional style. You do lots of things with side effect and heap allocated storage and whatever. And so there is some nice operators. There's your classic equals. There are arithmetic combinations of all of the equals. So you can say plus equals, minus equals, etc. I find that maybe use plus equals, maybe use minus equals. If you're starting to get fancy, just write it out. It's much clearer to write it out and not use these guys. The semantics of plus equals is A equals B. A yes. So it's just syntactic sugar. You can start to, like I say, if you go beyond plus equals, don't. Two other incredibly useful ones are plus plus and minus minus. Okay, these are auto increment and auto decrement operators. Very useful for writing loops. A plus plus put in some semicolons. So, and similarly, a minus minus is a decrements by 1. So, very handy.
Does that have the same syntax as in C with prefixing or postfixing the operator?
That's a good question, and to be honest, I don't know because I always use the postfix, and I haven't used the prefix in years and years. But yes, what he's referring to is the semantics of this are first you take the value of A. Actually, all right. These assignment operators are also expression operators, all right? Since they're both having a side effect, but they're also can be considered an expression. So you can do an expression like A plus B equals 3. All right, this is an expression. So what it's going to do is first assign B to 3, and then take the value of this, which is the value, by definition, the value of the thing you assigned, and combine it with A. All right, so this is going to have this expression is going to have 2 effects. It's going to assign B the value 3, and then it's going to compute the value A plus 3 as an expression. One thing to note about these operators is if you use them, if you do B equals A plus plus, okay, it's not quite, let me put a warning there, not quite this, in that the value that gets put into B is A before the increment. Okay, so the semantics of this are essentially B gets the old value of A, and then A equals A plus 1. All right. So it's a little bit weird. If you use it as an expression, you get the old value, but it increments afterwards. A lot of C technology also has grown up around these semantics. In Java, you would typically not use that feature. And the thing with ++, there's another version in C, which may or may not be in Java, because it is in Java?
Yeah.
Oh, okay. So the semantics of this are exactly the opposite. First, you do the increment, then you do the assignment, or then you compute the expression value. So the value of ++ A is you first do the plus, then you compute the value. The value of A++ is you use the value, then you do the increment. For your own sanity, I would pick one and stick with it. All right. So that is our set of operators. Now we can write all sorts of complicated stuff. There is, if you want to do more than two things, these are mostly binary operators, though you have unary subtraction to turn a number into minus. And certainly invert is unary and not is unary. They have a set of precedence operations which follow more or less what you would expect from mathematics, that times has precedence over plus and the like. My advice is don't rely on those precedence operators. You will undoubtedly not remember them. The way to group expressions is with parentheses. Parentheses have precedence over just about everything, and use them frequently. So if you want to write a compound expression of A plus B times C, or A plus, parenthesize it, be kind to the next person who reads your code. It doesn't take a lot of time, and it's good. Also, avoid, if you can, using assignment operators in expressions. Sometimes it's, if you really want to compress that code down to something really elegant, you can whack together all your assignments and your expressions. It doesn't compile any faster, and it's a little harder to read. So I would separate them out to, assignment, expression, just stylistically. Any questions? Are we going too fast, too slow? If you guys have comments or feedback or whatever that you think of, just send me notes, and we'll dynamically adapt the style and the pace and whatever.
A side effect is just a side effect that changes state or something?
Yes, a side effect is the term for, anything that changes a variable, anything that's not purely functional.
Why is it called side effect? That's one thing that bothers me. That's just the main thing you want to do.
Well, in something like A++, right? In something like A++, you really are doing two things. You're computing an expression value, and then you're changing the value. So if you are an expression-oriented kind of guy, then computing the expression is what you're doing, and the changing the variable is just some little side effect. Let's see. I haven't run out of things to say yet, so we're going to go on a little longer. Because this stuff is good. All right, we've gone through expressions. We now need statements. I'm trying to teach you most of Java today, so have patience. At least so you can write hello world and recursive factorial, which once you've got those working, everything else is just a matter of programming, as we say. Statements. I'll go through a few of the statements, the most important ones, for control. Okay, we've already seen statements in the form of definitions of variables, int, C equals 1. And assignments, oops, I need a new variable. C equals C plus 3, ubiquitous semicolon. We now have statements for control. So the first one is if, then, and the syntax of that is if, open parentheses, an expression. This is something that, actually it's more than an expression. It's something that evaluates to type Boolean. So it's some combination of things, can be arbitrarily hairy, except that at the end of it, it has to evaluate to a Boolean type. So you either start with Booleans or use a comparator. Let's see, let's use some meta syntax in here. Then you have put one statement following the if, exactly one, or a compound statement delimited by curly brackets. I almost always like to put in the curly brackets regardless. So say we still have our variables up there, C equals C plus 3. And we'll even put in an actual condition here if C greater than 0. So if C is greater than 0, this is going to increment C by 3. Excuse me for not coming up with a very imaginative program, but it's best to keep it simple at this point. You can, if you have, and here you can just put as many statements as you like. All right. If you have exactly one statement, you can get rid of that and do that. All right. I recommend against this because sometime you're going to come back and you're going to be debugging and you're going to say, gee, what is C at this point? So you're going to put some kind of print C in here, and then everything is going to be thrown off because now this is going to be the if, and this guy, even though it's nicely formatted and indented, is just going to be dangling, and you're not going to have any idea what's going on. You're going to be more confused. So unless you really forever and ever and ever in this program are only going to have one statement, I highly recommend delimiting automatically with curly braces. All right. Of course, we get else clauses. So the semantics are pretty straightforward. You test this condition. If the condition evaluates to Boolean true, you do this. If the condition evaluates to Boolean false, you do this. Okay. If you don't have an else condition and the condition evaluates to false, you just skip the whole body and continue executing at the bottom. So there's that. There's also, you can introduce here, an else if you want to start a chain of conditions. You can do this, ... else if ... else. All right, so this just tests, first does this test. If it's true, it does this. Otherwise, it tries the next test, blah, 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 down the line. All right. What other things to say about if? If you study the grammar of programming languages and if then else, you'll see there's an issue with attaching else's if you are free with your syntax. So you can say if C greater than 0, and if your statement is if A is less than 0, if B equals 3, and then you have else. Okay, now remember the syntax of this. The following if is one statement, and that statement is this if, and the statement, the body of this if is this if, and then say we actually put a body here and we have an else. The question is, does this if else go with this one, or this one? All right, and by convention, most programming languages define it to be this one, okay? The nearest one. But it is ambiguous generally in the syntax. The fact that I've nicely formatted it here is good for reading, but doesn't tell the compiler anything. So if you ever do this, always, 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 curly braces. Curly braces are your friend. This way, it's totally clear and unambiguous that this whole chunk is part of this if. This whole chunk is the part of this. So first use indentation to make it clear to fellow readers. Make it curly braces to make it clear to the compiler. And everybody's happy.
Can I just have one question about
Yes.
not directly related, but more the text editor we're going to use and how we get the right indentation of when we use Emacs?
I think if you put Emacs in Java mode, it will do the right thing.
Yes, Java mode.
Or tab. Tab will pretty much indent. Yeah, and I assume you have Java mode. So if you open a .java file, it will pretty much do the right thing, with the exception that it often inserts tabs rather than spaces. And if you do a lot of cross-architecture stuff, a lot of that stuff doesn't print out as nice as you would like when you move it to another machine. All right, ifs. Looping constructs. Very important to write loops. And basic looping construct, for loops. And the syntax of for loops is we have an expression which is usually an assignment or an initialization. I'll actually write it out as an example. Then there's a semicolon. Then there's an expression which is a test. And then there's a increment, a statement. And then curly braces, and then a bunch of code. The semantics of this are as follows. This is an I. You do this exactly once when you enter the loop. You then, each time through the loop, you test this condition. If this condition is true, you do the loop. Okay? When you get to the bottom of the loop, you do this thing. Okay? And the magic here is the semicolons. You can actually pack a lot of stuff in each one of these things. I don't recommend it, but you can. You do this condition. All right? And then you go back to the top of the loop. You test this again. If it's true, you do the code. You do this statement, and you jump back up. When this condition is false, you start executing here. Okay? And this particular loop probably accounts for 90% of the loops you will write. All right? This is a counting loop. It starts from 0, and this I less than n, if you work it through, this goes through the loop exactly n times. All right? When you are the first time through the loop, I is, of course, 0. The final time through the loop, I equals n minus 1. And when you get down here, I, if it's still in scope, is equal to n. All right? I recommend when you program counting loops, you pick a form. I like this one, and just stick with it forever. Some people like to do from 1 to I greater than or equals n. That also goes through the loop exactly n times. Some people like I equals n and count down. So you can do an I minus minus and count down. I particularly like this form. I recommend you find a form and you stick with it because it's tricky if you switch to count exactly how many times you're going to go through the loop, whether this should be less than or equals, whether this should start at 1 or 0. This form goes through exactly n times. As I say, that's 90% of the for loops that you will write or see. The other forms are things that have to do with objects and iterators, which we won't get to for a while. In C and C++, there's another form that iterates pointers, but we don't have pointers, so we're not going to do that. All right, cool, almost done. Final loop that I'm going to talk about, or control statement, is the while loop. It's an even simpler one. While condition. All right. This evaluates the condition. If the condition is true, it evaluates this code. Otherwise, it just jumps to the end of the code. Every time it gets here, it reevaluates the condition and continues here. So the only way you're ever going to get out of this is if this condition changes. Assuming you get into it to begin with, this condition has to change. So somewhere in here, eventually you have to, change some variable that affects the condition. And this is good for running through data structures where you're not sure ahead of time what the size is, so you can't use a counting loop. You just kind of grovel your way through till something happens or you detect something. Say you want to go through a character string or an array and stop the first time you encounter the letter Q. You just go, blah, blah, blah. You just have your condition. If this letter equals Q or not equals Q, you quit. So anyway, yes, if it equals Q, you continue. So anyway, I'm getting my Booleans mixed up, which I sometimes do. But if this is true, you do the loop. If it's false, you don't do the loop. Which brings up something, as I say, here, the only way this is going to change is if you change it in the loop, or a lot of times you use this for external things to happen. Say you're talking to the network or waiting for some external device to do something. You can put this test here and wait until somebody external to you makes that thing true, and then you go. The bad part of that is you can end up spinning a lot. In this sort of loop, there's nothing to prevent you from changing this counting variable inside this loop. So I could say I equals I plus n and instantly drop out of the loop. People who do this, the loops that do this are very confusing. So in general, don't touch your loop variables inside a for loop. You pretty much have to inside a while loop. What else can we say? There's two things which I guess I'll leave to Alan to talk about in recitation to give you fine-grained control of for loops. There's two things, special commands you can put inside called break, a break statement. Usually you'd have something like if. Okay, break says, when you hit break, it says immediately quit the loop. Okay, so here if I equals 3, break, that means this guy is only going to get up to 3, then it's going to break. There's also one called continue. Continue says, don't do any of the stuff in the loop below me, go immediately to the test, and then start the loop again. Or to not the test, to the increment and start the loop again. So they're just help you fine-tune your loops. Hopefully, well, they're good to have. Now, we have two looping constructs, which seems a bit redundant, and it is redundant. For example, we can rewrite our for as a con, or while rather. That for is identical to I equals 0 while I less than n, curly braces, stuff, and then I plus plus. Okay, sometimes when things start to get a little hairy writing even count loops this way, you can transition to this form. And clearly a while loop is just a for loop with nothing here and nothing here. So it looks like, yikes, for semi, condition, semi. And that's just exactly a while. So they are redundant, but to somebody reading your code, they mean different things. So in some sense, when you're writing your code, you're telling the person reading it a story. And so these just help you write your story. All right, almost done. I want to teach you how to write hello world and recursive factorial, and then we'll go. Since if you want to fool around with this stuff, you at least need to be able to do a basic program. Unfortunately, a basic program in Java requires a whole pile of mechanism, which you're just going to have to treat as pure magic right now. All right? So, let's see. Java doesn't let you just open a file and write a procedure or a method. It wants everything to be in a class. And since we haven't talked about classes yet, you just have to take my word for it that there's some magic. So here's the magic. All right, public class hello. This defines a class called hello. And the Java compiler being the way it is, it's going to want to see that in a file called hello.java. It is very snippety about your file naming and class naming. So, plus, it is case sensitive in everything. So make sure you capitalize exactly the same way. That's true across the language. Variables, method names, everything is case sensitive. So, and traditionally, class names begin with a capital letter. That is not enforced, but it is traditional. Some more magic. Most of Java is writing keywords which have very little to do with actual execution of the program. All right, so this declares our the routine we actually want to write. We have to define, for every routine we write, we have to define routines just the way we define variables. And routines have types, which are both the arguments they take. This is an array of strings. Don't worry about that syntax. But here's our magic void type, which just tells us the routine main does not return anything, so don't expect it to return anything.
Is that string, square bracket?
Yes, a string square bracket args. It doesn't matter what you call this. This is a dummy variable, but main is the magic word. It is defined by the system or declared by the system as main. In C and C++, it's also a magic word. It's basically where to start. You always need a magic place where to start. And in all these sorts of languages, you start at main by tradition. And main is also typed, insisted by the Java system to be typed to have string. This, you get the command line args in that string. So that's what that does. All right, so we have main. And now we want to print something. And unfortunately, to print something in Java, you need a lot of mechanism. But it's just a magic incantation. And finally, we get hello world. All right, that kind of, let me rewrite that. It kind of peeled off into our operator set here. All right, so this program, to compile it, you would write on your console, assuming you have Java, you would write javac hello.java. And this, if you typed it correctly, will produce a file called hello.class. And then to run it, you would type Java hello. And what this tells the Java runtime, this starts up the Java runtime, tells it to go look for class hello. Okay, Java has this very class-oriented view of the world, and that's where this naming scheme comes in, because it says, okay, in order to find the class hello, I need to look for a file named hello.class. So it'll go look for that file, start it up, and it should print out on your console, hello world. This piece of magic, system.out.println, is the command to print a string on the console followed by a carriage return. So it gives you a new line at the end of the line automatically. Yes?
Does each Java file just have one class?
In general, yes. It has one publicly accessible class. You can put hidden classes in there, but only one publicly accessible class. I know it's a royal nuisance because if you have a lot of small classes, you have a zillion little files. And if you have one of these integrated development environments which keeps track of it all and hides it all from you, it's not so bad. But if you're using Emacs, it can be a horror. All right, almost done. It's time for, we'll do recursive factorial. So another program, again, we'll start with some boilerplate. And now our actual routine. So you need always a return type. And if you have arguments, all of the arguments have to be typed. And if we had multiple arguments, it would be int a, char b, comma, dot, dot, dot. Okay, separated by commas with the type, then the name of the variable. Type, name of the variable.
Could you do, if there was interest, could you do int a comma b or?
No, you have to put a separate thing. Certainly in declarations here. And this is our classic algorithm here. If it's less than or equal to 1, return 1. And here I'm going to violate the rule I told you about always using curly braces and not use them. And that's it. So some new things we introduced here is the return statement, okay, which is only valid inside of a method. And it says, as soon as you hit this, you return from the routine. And the return value that you return is the thing following it. I always surround the return value in parentheses, but that's just me. You do not have to, but I always do. But it's basically return followed by an expression. So this says if a is less than or equal to 1, we're going to return 1. Otherwise, we're going to return a times, and here's our recursive call. Function calls in Java are function name, open parentheses, argument list. So it's kind of pretty much the same as Lisp, except you take the function name outside the parentheses, and you separate the arguments by commas again, comma-separated lists instead of space-separated lists. And now, of course, this program, this is a class, but it doesn't have a main, so it's not going to do anything. So in order to do this, we need to go put a main. And then we'll just do, well, we'll make it a little clearer. Int a equals 7. Int fa equals fact of a. And then we'll do our system.out dot println of f of a. All right. Now, there's a little bit of magic here in that here I'm sending a integer to println, and println is smart and will try very hard to do the right thing with a variety of types. So it will basically, if you pass it a variable of type integer, it will say, you're passing me an integer. I'm going to use the integer print thing I know about, and we'll print it out correctly. We'll talk about that magic more later in the week, but you can use it to just print out a raw integer.
I assume it's more complicated, and that's why we're not doing it, the args, so that you could just say, call fact from the command line with a number.
Yes, yes. We could. All right, if you would like to see that, it would look something like all right, this takes the first command line argument and calls this piece of magic, which turns it from a string to an integer and puts it into A. That's a little too much magic for today. We'll go with 3, which is a much simpler expression. All right, that's all I have to say. Are there any questions? Yes?
Do you need that interim stuff? You can't, maybe I misunderstood you. You can't just call f of a as being fact of 3?
Oh, yeah. I could get rid of all these things and expand that whole thing out into that statement. So yeah, I could do this equals fact of A, or I could do the whole thing at once and say this equals fact of 3. Or I could say this equals fact of integer dot parseInt of args of 0. But at some point you want to break things out and just make it clear what somebody's doing. So this is a lot of stuff, so any questions?
If I go back to what's at the top of the board there, the int a char b thing.
Yes.
I think I missed what you were doing there.
Oh, okay.
What is that?
Here I'm defining a routine with only one argument. Okay, and here I'm calling a routine with only one argument. But for example, if I was writing Fibonacci, well, that's not a good example either. But say I was writing a add routine for something, which you'll do in, say I just wanted a routine that would add 2 integers instead of calling my plus operator. Okay, I need a routine that takes 2 integers, and that's how I declare it. And then when I call it, I'm just going to say add of 2, 3. Okay, that's the call. So all I was getting at was argument lists are A typed and B separated by commas. And when you call things, you separate the actual parameters by commas, and you don't put in the types.
Is the order of those methods important?
No. The order of the methods is not important. Of course, the argument of the order of arguments is. Java is not a keyword argument language. It is a order argument language. So everything has to be in the same order. The compiler will check to make sure that you give it the right number of arguments and the right types of arguments, but it can't check to make sure they're actually the right arguments. So.